All right, hello everyone. If you've ever typed something, seen that little red squiggly line, and wondered how your computer knows what you meant to say, well, you're in the right place. We're going to dive into a fundamental concept called minimum edit distance. We'll break it down nice and simple so you'll be completely ready to tackle it on your next exam.
So here's our roadmap. First, we'll get a handle on what the problem actually is. Then we'll look at the obvious solution and see why it's a bit of a performance trap. That will lead us to the much cleverer dynamic programming approach. We'll even build one of the solution tables together, step by step, and we'll finish up with the key points to remember and some real-world applications.
Right, let's get started. Section 1, the edit distance problem. It sounds a bit abstract, doesn't it? A distance between two words? What on earth does that mean? Let's get a proper definition.
At its heart, it's actually just about counting. We're looking for the absolute smallest number of changes, or operations, that we need to perform to transform one word into another word.
And importantly, we're only allowed to use 3 specific tools to make these changes. We can either insert a character that wasn't there, delete a character that was there, or replace one character with a different one. That's it. Those are our only moves. So let's take a very straightforward case. How do we get from cat to cut? Well, the C and the T are already in the right place. All we have to do is swap the A for a U. That's one single replacement operation. So the minimum edit distance is 1. Let's try another one. How would you turn DOG into DOO? Well, you just get rid of the G, wouldn't you? That's one deletion. So again, the distance is 1. These simple examples are the foundation for what's coming next.
Okay, now your first instinct as a programmer might be to think, I can solve this with a nice, simple recursive function. And you could, but you'd be walking straight into a very common and very slow trap. Just imagine a more complicated conversion, like from kitten to sitting. A purely recursive approach would start calculating all sorts of smaller problems, like the distance from kit to sit. But because of how it branches, it would end up calculating that same exact subproblem multiple times. It's doing the same work again and again, which is just horribly inefficient.
And this is the crucial difference. The recursive approach on the left seems intuitive, but it's painfully slow because it repeats so much work. On the other hand, dynamic programming is systematic. Its secret weapon is that it stores the results to these smaller problems, so it only ever has to solve each one once. It's much, much smarter.
So let's get into this smarter approach. Welcome to dynamic programming. The whole magic here is that we use a table. You can just think of it as a grid to build our answer piece by piece in a very organized way. Now, every single cell in this grid has a very specific meaning. We'll call a given cell DPIJ. All this represents is the answer to a smaller question. What's the minimum cost to turn the first I characters of our starting word into the first J characters of our target word? Each cell holds the solution to one of these many problems.
And this is the engine of the whole thing, the logic for filling out the grid. For any cell, you look at the 2 characters it corresponds to. If they match, brilliant. There's no cost. You just carry over the value from the diagonal cell. But if they don't match, you have to perform an operation, which costs 1. So you take 1 and you add it to the minimum value of its 3 neighbors, the cell above, the cell to the left, or the diagonal.
Right, that's enough theory. The best way to really get this is to see it in action. So let's build the table from scratch for our cat to cut example. The very first thing we do is initialize the table. We put our words along the top and side, starting with a blank space for an empty string. That first row represents turning nothing into our target word, which is just a series of insertions, so the cost goes 0, 1, 2, 3. The first column is the opposite, turning our source word into nothing. That's all deletions, so the cost is also 0, 1, 2, 3.
And here is what that setup looks like. To get from an empty string to C costs 1 insertion. To CU, 2 insertions. To CUT, 3 insertions. Same logic for deletions going down the first column. This setup provides the base cases, the known starting points that the rest of our calculation will build upon.
Now let's fill in an actual cell. Let's take the one that corresponds to converting CA to CU. We're comparing the characters A and U. Obviously, they don't match. So we apply our rule. We look at the 3 neighbors. The cell above has a value of 1. The cell to the left has a value of 1. And the diagonal cell has a value of 0. The minimum of those 3 is 0. We add 1 for the cost of the operation, giving us 1. So a 1 goes into this cell.
And you just repeat that process. You apply that same simple logic for every single cell, working your way across and down. Each answer is built upon the solutions you've already found for its neighbors, until the entire table is complete.
And when it's all filled in, the answer to our original big question is always sitting there, waiting for us in the very bottom right corner of the table. The minimum edit distance to convert cat to cut is, as we see here, 1.
Excellent. So now that we've seen how it works, let's just quickly review the main points, highlight some common mistakes you should avoid, and talk about why this is more than just an exam question.
All right, a quick tip for when you're under pressure in an exam. These are the classic trip-ups. By far the most common is simply forgetting to add the 1 when the characters don't match. Also, be really careful when you set up your table. If you get that initial row or column wrong, every other number that follows will be incorrect.
And what about performance? The complexity analysis here is quite straightforward. If our words have lengths m and n, our grid has m by n cells. Since we have to visit every cell to do a little bit of work, the time complexity is proportional to the size of that grid, or OMN. And since we have to store the whole grid in memory, the space complexity is the same, OMN.
And please remember, this isn't just an abstract exercise. This exact algorithm is working away behind the scenes in so many things you use. It's what powers spell checkers, it's what diff tools use to show you the changes between two versions of a file. It's even a crucial tool in bioinformatics for comparing DNA sequences. It's incredibly useful.
Okay, time for a final rapid-fire review. If you're cramming, burn these 4 points into your brain. 1. Distance is the minimum inserts, deletes, or replacements. 2. We use a table so we don't solve the same problem twice. 3. The rule is, if they match, take the diagonal. If they don't, it's 1 plus the minimum of the neighbors. And 4. The final answer is always in the bottom right cell. If you know those 4 things, you're in great shape.
So I'll just leave you with a final thought to mull over. This grid-based technique of breaking a big problem down into a lot of smaller, overlapping subproblems, it's one of the most powerful ideas in all of computer science. We've used it to compare strings, but what else could you use it for? What other kinds of complex things could you compare this way? Have a think on that. All the best with your studies.